midterms grade, basin mga next week pa ko maghatag ninyo ang midterms grade. I'm still checking. Wa pa ko na human kay 90 mo kabuok. So daghan jud kayo plus the problem sets pa no. So most likely next week pa siguro ni siya. Hopefully no. Ang kaning next set is today is our first meeting after sa midterms exam na to no. Pero we're still on track. Kay today is this week I think we are week 5 or week 6 no. We will be dealing with structures na siya forces no. Usually atong gisolve before is wala siya mga external force. So karon kay will be we'll be solving with forces na. And unsa may implications ato niya, no? So April 6, which is today, is we'll be discussing two-part series ni siya. Because I don't want to overload ninyo na daghan kay information. So that most of you or maybe all of you siguro nakapalit og kanang notes ni Sir Gitamundok no. So ako na i-share akong screen no. So alright. So I think it should this one no. So I'm pretty sure na amoy notes copy sa notes sa kang engineer Gitamundok no. So we'll be discussing chapter 3. And kani si chapter 3 medyo taas kini siya. I would be breaking it into 2 sessions for us to digest. So I'll be slowly deriving all of these equations and sa may meaning ani the graphs and stuff kung kinabata mag explain sa graphs no. So we'll be dealing with this one. But of course, 2 parts ni siya. So we'll be kanisha, this is another reference for you to read no sa kani atong discussion, but of course mo balik ta sa katong ako ang main book which is kang Mario Paz no. So I'll be explaining this one but I won't be 100% reading this one because I have my notes here no. So mo unsa to no, I'll be altering my style for today or for this week no, for April 6 kay hopefully this will be effective sad no. So wala ko nakataog notes specifically sa inyo karon. There are several reasons but the important reasons is I want to try na wala dili ko maghatag notes and then later on if after the meeting mohatag ko partial sa ko notes no. But of course I'll be explaining my lecture no hinahina and then kaning ako ang isuwat karon is mo siguro ako ihatag ninyo. Okay, so mo to siya regarding sa midterms, mo to siya most likely next week pa. I'll try to make it in time no. Most likely delayed na ko but daghan pa kay ta wato no. So 6 and 13, April 6 and April 13 would be our lecture sa chapter 3. And then 20 and 27 kay ang last chapter na ta, which is dili kayo siya bugat. If you understood chapter 1 to 3 then ang chapter 4 which is kanang kung if you follow Engineer Gitamundok's notes is it's not chapter 4 no sa kuha. So chapter 4 sa iha is response to periodic loading, and then I think ang chapter 5 is impulse impulse loading, and then ang chapter 6 is I think triangular loading if I'm not mistaken. Chapter 6 is response to general dynamic loading no. So ang last discussion nato is sa 20 and 27 will be diretso sa chapter 6 sa notes ni Engineer Gitamundok. But for me, my reference is Mario Paz, so it's chapter 4, no, generalized loading. So ang kanisya sa chapter 4 and 5 sa notes ni Engineer Gitamundok, it's additional readings for you guys. Kay I'll be briefly touching this one, no. dili kayo sobra ka in-depth pero briefly touching it lang kay the knowledge that you need to know is Fourier transform, no? And then I think this is quite difficult sa if wala mo kagi sa advanced mathematics or sa differential equations, medyo difficult ni siya to understand. So I'm trying to simplify it by using another technique, no? But it's the same answer, just different lang ang pamaagi niya. So moto siya, that will be 20 and 27. So the problem sets mugawas inika April 13 sa problem set 3, and then ang problem set 4 would be at April 27, no? So you have kung 13 mo hatag ko, so the deadline is 27. So if I will be sending you sa 27, sa 20 for the problem set 4, which is the last problem set, the deadline is 27. So you have like 7 days to do it, no? Pero task ka po ng 7 days kay daghan matag holiday sun. Okay? So moto siya. And then so I'll be discussing sa ato ang tawag ani lecture karon, no? So balin ka dire. So I'll be using another app for this one. And then before I start, dapat may question or clarification before we start, no? Regarding sa news lang sa. So wala ka masiguro reaction. Okay, so mo to siya, no? So I would advise now take notes during sa kanin lecture so that more at least naka-follow along ka kitang tanan, no? So we'll be dealing with harmonic excitation. So harmonic excitation. So kani si harmonic excitation kay this is what you call your periodic loading, no? But we'll be discussing first the undamped system sa. Alright? So undamped system lang sa ta because that's the easiest one, no? So mobalik ta sa ato ang the usual nato, no, na free body diagram, which is kanisha. Our on to, this is the spring, and then this is the damper, and then ligid siya. Don't mind the layo kayo ang ato ang floor and the wall. I'll make it a little bit close, no? Perfectionist gyapon ni siya and stuff. And then now we will be discussing. We'll be discussing this one na. So nanatay force P, no? So in harmonic excitation, kani si force P, no? Kani si force P, we will be I'll be setting this P is equals to FO, which is the amplitude of your force. So the maximum amplitude, no? So times the sine of omega bar E, no? So meaning ani niya natay force FO pero subjected to a forcing tawag ani kanang sinusoidal na loading, no? So the force will be like kung natay time history, no? So I'm going to make this very crude na drawing. More siya if this is our positive force and negative force, no? So more siya atong force kay may nana siya mo sine wave siya yung itsura. Okay, what happened? Anyway, so it's a sine wave ang atong itsura, ano? So moto siya, no? So the differential equation nato karon, the ODE, our ordinary differential equation for this system is same gap, no? So mass times acceleration. So I'll just say na kani siya na direction is u, no? So u double dot plus c, which is the damping constant nato, and then times the velocity plus your k, which is the spring stiffness, no? And then times the displacement is equals to FO sine of omega t, no? Omega bar t. Okay, so mo ni atong starting point. So karon problematic na, no? Okay, we have a right hand side, no? So we will be solving for the ordinary differential equation in two separate steps, no? Which is the first one is we will be solving ODEs, the characteristic equation, and then we will be solving for the particular equation, no? So for our characteristic equation, no? So the characteristic equation, yep. Okay, where's my mouse? There we go. Characteristic equation, no? What will happen now is we will be solving for this one, no? Since we'll be dealing with only undamped lang siya, undamped, and then free undamped na harmonic na loading, we'll be dealing with the free vibration lang siya. Then later on we'll be discussing with the damping, no? So if we're going to solve this differential equation, no, sa kanisya, hopefully you still remember, no? So the solution for the characteristic equation, no, UC of t is equals to A cosine of omega t plus B cosine of omega t, no? Hopefully you remember this one. So ang kanisya is gikan ni siya sa ato ang under damp na solution, no? Because we will, as I discussed before, data mag overdamp kay rare kay lang structures na overdamping. Usually our structures is underdamped atong structures, no? So this is our solution, no? So where our omega is still the natural frequency, no? So k over m, the square root of k over m, mo ni meaning anak niya. So now, since we already know this one, the characteristic equation, so we're now going to solve the particular equation, no? Or the specific solution. So depende on sa inyong ganahan, no? So I'll just write this one as particular solution. No? So the particular solution is, if you still remember sa atong differential equation, but before that, murag, just to be sure lang, no? Can anybody hear me? Kasi na story ko walay sound, no? All right.
Yes, sir.
Okay, sige. So hopefully wala kay background noise kay akong miming si scratch sa kuha, sakit kayo. So anyway, okay, so particular solution ta, no? So if you remember sa atong ordinary differential equations na class, we have several methods on solving sa particular solution, no? So ang the most easiest one is the using the undetermined coefficient method, no? So using undetermined coefficient method. So kani sa undetermined coefficient method, no, is the most easiest one because we will not be dealing with a lot of integrals and differentials, no? And then pero trial and error na siya, unfortunately. But another way to solve this particular na solution differential equations that is using the variation parameters, no? So whatever works or most comfortable sa inyo, okay, you can use what is comfortable. But for our discussion, I'll be using the undetermined coefficient method, no? Because number one, it's easy, no? So dili kayo kanang I don't need to explain a lot of things because we'll just use simple algebra, no? So if we recall sa atong undetermined coefficient method, we need to use a trial solution, no? So akong trial solution, which is I will say na u p of t is equals to, since ato ang ordinary differential equation kani siya sa right side niya kay na siya sign, no, sign na function. So that tells me that maybe ang solution niya is na siya sign function, sad, but I'm going to introduce a undetermined coefficient, which is a, no, or maybe dili siguro mayo a, let's say c na lang, no, c na lang, c1. And then of course we'll also be introducing this one as well. Kung nakatay sine, nasa tayo cosine, right? Because if we're going to integrate, if you're going to get the differential, no, of this equation, no, mugawas man siya sine and cosine. So we need to cover all possibilities, no. So if you're going to get the first derivative of our trial particular solution, what will happen is this will become cosine of omega t, no, times omega plus c2 negative sine of omega t times omega, no. Hopefully you can follow, no. So getting the second derivative as well, mahitabo ani niya omega squared, no, cosine, that cosine, this should now become negative sine of omega t, okay, minus c2 omega bar squared cosine of omega t, omega bar t. So if we have this particular solution, no, kani siyang tulo, we're now going to substitute sa atong particular solution sa ato ang original na solution, which is kani, right? So that's how the undetermined coefficient works, no. So ako isuwat diri, substituting the particular equations, no, of t to ODE, our original ordinary differential equation. What will happen now is sa sa atong mass times ang second derivative, no, of our trial solution, which is negative c1 omega bar squared sine of omega bar t, no, minus c2 omega bar squared cosine of omega bar t, right? And then plus k times c1 sine of omega t plus c2 cosine of omega t is equals to, kaliswat lagi sa ubos, is equals to FO sine of omega bar t, right? So what will happen now, or what we need to do now, is we need to find the constants, no, C1 and C2. So mo magit ato ang goal karon. So atong buhaton is to find the constants, we need to natin mo kag hint, no. So the hint now is natay sine of omega t. So kaning sine of omega t ato na i-pares tanan sa sine of omega t sa left hand side sa equation. And of course, hidden is the 0 cosine of omega t. Hopefully you did not forget, no. So meaning ana niya, we can we can equate these sine, no, with the sines here sa left side sa equation, and then the cosines to the cosine sa right hand side sa equation. But if you notice, no, I'm going to write it na lang para just to be clear, no. So I'll try to solve first the C2, no. Sa C2, ang mahitabo ani karon case negative C2 omega bar squared there we go, plus C2 sa ani siya is equals to 0, right? So ang kani siya tanan term, we can therefore say that C2 is equals to 0, right? Okay, C2 and C2, no? So it doesn't make sense, right? So Wato siya. So we now know that C2 is 0. So ato i-focus karon kaning unsa to? Kaning sa sign, no? So mag try ta og find ang C1 no from using the sign, no. So mahitabo ni karon kay I'll distribute sa so m negative m C1 omega squared 2 squared omega bar squared, no, sine of omega t. Then I'll just disregard the C2 because we already know na wala gid siya, no? Zero ang iyang value. So k C1 sine of omega t, so is equals to FO sine of omega t. So mo na siya. So we will just cancel out the sign, no? So what will happen is negative m C1 omega bar squared plus k is equals to f of kc1 is equals to FO sine of omega t. Okay, so to find for C1, ang mahitabo ni karon kay I'll just factor out C1. So negative m omega bar squared plus k is equals to FO sine of omega bar t. Okay, so C1 is therefore FO sine omega t, omega bar t, divided by negative m omega squared plus k. So this is our constant C. So therefore, the complete solution to the of the different ODE, the ordinary differential equation sa free vibration is U of t, no, is equals to a sine of omega t plus, sakta ba? Was it sine? Okay, sine, no? Sine of omega t plus b cosine of omega t plus ang FO sine of omega bar t divided by negative m omega bar squared plus k. Since this is C1, I have to multiply C1 by kani, no? Times sine of omega bar t. So this is our complete solution, no? Let's see. Okay? So, actually, nasobra ko. Nakabutang yung pag-ugsay, no? This should be cancelled out. So, kani siya. And then, our complete solution is kani. So, nasobra ko times. But anyway, it's okay. So, gonna fix a little bit of this. Move it here, maybe. Di lang. I'll just rewrite it, no? So, this is FO. Okay. So this is our ordinary differential equation or the solution, complete solution, no? But of course, we have to solve for A and B, no? Because these are the constants of integration. Okay? And the only time that you can solve this one, ang kaning A and B, kung natay initial value problem, no? So initial value problem or initial boundary condition. So sa structural dynamics, it's usually IVP, no? So initial value problem kay muhatag man ta og kanang initial conditions niya, which is when at time 0, usually the displacement is 0 and then your the velocity is also 0, no? So that's what we are going to use, no, to solve for A and B. Okay? So but before that, no, before we're going to solve A and B, I want to clarify ang kanisiya, no? Kanisi omega bar, no? So, usually, what we do in practice as well is we want to convert our omega bar, no, into some sort of an omega lang because if we have omega here, no, I think it's tawag ani ka na mas easier to interpret in terms of natural frequencies lang. So what I'm going to do now is I'm going to introducing our factor, no, the factor r, no, as the ratio between the applied forcing frequency to the natural frequency. And what I mean by this, no, is it's just a fancy term that saying na mag-introduce ko ratio R as the forcing applied force frequency, no, divided by our natural frequency. Okay? So again, no, so ang kani siya si forcing frequency omega, no, it's how frequent or how fast, no, is the load being applied to the system, no. And the natural frequency is usually it's a property that we all know na it's the square root of k over m, no. So that's the natural frequency. And this sa una kay ato man isolve kay sa may purpose sa natural frequency, and then why is it very important, no. So later on I'll be discussing sa importance na kay na naman kay force. Okay? Then unsay mahitabo, no. So if I'm going to introduce R to the equation, the ODE will now become what's to? U of t, no? So our equation of motion or displacement is still a cosine of the natural frequency omega t plus b sine of omega t plus FO over, so since what we can do is if we want to relate this to R, no, so I'll just write this first, Anisha, no, and then sine of omega t, and then asa nigikan, no, so you're going to rewrite it is just R times omega is equals to kami siya, no? So, ang nahitabo man sa tong equation, here, kani siya, it's omega squared. So since this is omega squared, I will be squaring the both sides of the equation, no? So, omega squared is equals to R squared omega squared, no? So, what will happen is, if we're going to substitute ang kanisiya to here, kanisha, and then factor it out, no? Ang factor ang k out, no? So the resulting solution, resulting form would be kanisha. Alright? So mo na siya gikan, no? So at least clear ni siya. Okay? So now to solve for the constants of integration a and b. Okay? So ato na i-apply atong knowledge at time is equals to 0 seconds, no? Our displacement is equals to 0, no? So it can be inches or it can be millimeters, what have you, no? So we'll just be consistent, no, sa atong units when the problem comes, no? So for this one, since this is we'll treat it as unitless lang sa because we don't know any units for now, no? So what we'll do is ato equate kanina equation, this equation, no? And then ato i-set to 0. Okay, moment ang kanisya na initial boundary condition. So 0 is equals to a cosine of omega times 0 plus sakto ba? Times 0. Yes, yeah. So b sine omega times 0 as well, then plus FO over K1 minus R squared times sine of omega bar times 0. Okay? So, tanan mga sign, okay, mahimong siya 0, right? No? And then, kani siyang cosine will become 1. So, therefore, ang atong A for this initial condition is 0. No? It does not mean that tanan 0 ni siya. No? So, kani siya sa kanina particular na problem, usually common in structural dynamics, usually given atong initial na displacement and initial velocity, no? Pero if the problem says na itagaan o ka ng initial velocity or initial acceleration ba or initial displacement, you have to go back to this equation and then resolve it, no? So, moving on. So, kibaw na ta kay A is 0. So, at time 0 sad, we know usually that the velocity, which is our O prime, no, is equals to 0 as well, no? So 0 meters per second or feet per second, inches per second, no? So what we have to do first is we have to get the first derivative, no? First derivative of our solution, which is the derivative of cosine, so A omega negative sine, no? Because the derivative of cosine is negative sine, no? So plus B times omega cosine t plus kani siya, this is all a constant. Constant ni siya tanan, so mag-remain siya FO over K 1 minus R squared, and then times the omega cosine of omega RT. Okay? So, from here, ato is set to 0. 0 is equals to, kani siya, no? Negative A W sine of omega times 0 plus B omega cosine of omega times 0 plus FO over K minus 1 minus R squared. Extend this one like so, and then natay W bar or omega bar times cosine of omega bar times 0. So, ang may tabuan ni karon kay we all know as ang A is still 0, no? 0 ni siya. So, we'll be solving now for the B, no? Ang constant B. So, I'll bring this to the left side. So, mahulog siya na negative B omega bar over K times 1 minus R squared is equals to FO omega bar over K 1 minus 1 minus R squared times, well, cosine of 0 is 0, so kani siya, no? So, solving for B, so FO, okay, since, let's see, nasa ko copy, it should be, kanina siya. There we go. Okay. Sobrahan ko copy that. Okay, negative B omega bar. So, B now is FO over K1 minus R squared. So, therefore, let me check first sa akong notes, no? Okay. Omega, so, this is wrong. Kanisha should be walay bar. So, ang kanisha will become omega bar divided by omega is R. There we go. So, this is our B na corrected, no? And then the equation, no? The equation is now U of T. So, wala man tayo A, no? Is equals to FO R over K 1 minus R squared, and then mag-multiply ta og sine of omega T, no? And then this one is negative. So, kani siya negative sa siya. then plus FO over K 1 minus, 1 minus R squared sine of omega bar of T. Okay, so let's simplify. So the total response or the displacement now is kanisha FO over K minus 1 minus R squared, no? So nag-factor out ko ani niya, and then what will happen now is kanisha, since this is positive, mo na kong suwaton first, kanisha minus R sine of omega T. Okay? So this is our equation of motion, no? So kanisha, this is our equation of motion for undamped with harmonic na loading. So at any point in time, U of T, no? Natay kanina equation, but you have to take note na ang kanisha, kaning sine omega minus R sine omega, no, T. So natay duha ka different terms, no, which is are subtracting to each other. Pero what will happen in the practical sense, no, ang kanisha kaning R sine omega T bitaw, usually sa tong structures kay nagit siya inherent na damping, which is kanina term, this term would become negligible if ato nag-i-introduce og damping, no? So in the most practical sense, no, sa atong structural dynamics na class, kay we can actually disregard the R sine of omega T. So therefore, the forcing frequency, no, term, the forcing frequency term so it will just become U of T. So mahitabuan ni siya na FO over K 1 minus R squared sine of omega T, no? This is what you call your steady, if kamo ko mag-spelling steady state na response, no? Ang meaning ana sa steady state response is it is the response na kanang dili siya kanang tawag ani kanang it's a force that di hatag siya o kanang steady state. So I'll explain it further later on. So if we have the transient sad, no, sa transient na sad nato na response sad, no. So it is interesting, no, kay kani si R is balik ta ang definition ani niya is the cyclic, no, or the cyclic function, which is the omega bar divided by the natural frequency. Okay, so what that means is if ever our forcing function, ang cyclic behavior sa forcing function omega bar is equal to our natural frequency, meaning ano niya, if it is equal, it will become to 1, no? Then ang mahitabaan ni karon is our amplitude of motion, no? So ang meaning sa amplitude of motion is the pinakadakop og displacement, no, sa ato ang response, no, will become really or infinitely large. So mo na akong gimin na if we're going to solve or design a structure, unta ang ato ang natural frequency the natural frequency of our structure dili siya mo coincide sa ang frequency sa ang cyclic frequency na pag-apply sa loading. Kay if ever mo siya ang case, ang mahitabuan ni karon kay our amplitude of motion or our if ako na i-layman na lang, no, so mohatag siya og dakog stresses, no, or infinite na stresses because your forcing function and your natural frequency na coincide, so it's gonna become bigger and bigger, no, over time. So this is what you call a kana resonance, no, na resonate siya with each other. So it's a very important na tool for us to know our frequency ratio. Kaya if maka 1 ganit na siya, patay gyud ani. So meaning ana sa 1 kay na-resonate siya. So it's okay to be to dako siya ang ato ang R or lesser siya, usually it's hopefully it's lesser, no? So the natural frequency of our structure is greater than our forcing function, which is usually the case, no? So if mo na siya, then the structure can withstand the loading. So money meaning sa R, no? And the importance of our natural frequency. So ito siya, no? So hopefully that gives you an idea na nag-sige tag-solve og differential equation, pero that idea alone na kanang kailangan ang natural frequency of the building should not be equal to the forcing function. It should own that, no? That idea alone is very powerful. Kay if we analyze earthquakes later on, if magmasterals na mo, if we analyze earthquakes, kay we have what you call a what you call a fundamental frequency. So kanang unsa to, kanang tanan ato ma earthquake data ana siya sa displacement chart, and then so this is the displacement, no? So this is time, and then this is the displacement with respect to time and whatever, no? So kana siya na graph na siya na if you're going to apply a Fourier transform, no, mugawas siya og some sort of like a histogram, no? So histogram siya na siya. And then ang katong pinakataas na frequency sa after you convert it into a Fourier na graph, ang pinakataas na frequency is what you call the fundamental frequency. And that fundamental frequency, another way of thinking about it is that fundamental frequency is your frequency sa omega bar, no? So that's how the earthquake is striking you most frequently. So if ang omega bar, which is the fundamental frequency sa earthquake, kay nag-coincide pagkit siya sa ato ang natural frequency omega, no? So most likely it's your building will fail, no? Because mo gina siya, mo resonate man siya, no? So that is why natay notion na usually ang mga high rise compared sa mga short buildings, usually kung nasa earthquake na forces, usually atong yun kay hala atong high rise kay mo gina matumba una kay mo ni taas, no? And then usually ang mga shorter buildings kay okay ra kay ato ang natural period is very big, no? So dili kay siya mo vibrate as much, right? And then ang low usually is the mid-rise building, mga 7-story, 6-story, 8-story. Kay natay several news na assessed from sa Philippines dito sa gawas, no? Ang mga high-rise and low-rise ang ni okay, pero ang usually ang natumba daw is ang mga mid-rise. It's because of this phenomena kana siya, no? Kaning atong omega, no? So we have to take note that if we're going to solve for earthquake na forces, how once we go into the design na gid siya, we have to take note of this one, no? So that's structural dynamics, no? Usually what we do sa ato ang computing for earthquake loading, it's usually static case raman, which is allowed by the code sa NSCP code or even the ACI code. But if we go higher and higher, the dynamic response is much critical, no? Kay di matakhibaon sigid ang iyang real behavior na, no? So di na musulod ang atong dynamic analysis, no? So the dynamic analysis is a fancy name of saying that we have to do what I've just discussed, no? And then hopefully katong mga forces that we will be deriving later on sa ato ang discussion, katong mga additional forces or additional moment, kay mo atong gamito na design moment sa ato ang design moment and design shear sa ato ang building, right? So mo na ato ang i-try o kanang understand sa pagkakaroon, no, kanang the importance of the forcing function in relation to the natural frequency. Okay? So, sa pagkakaroon, no, before I move on, before I move on, nabatay questions sa undamped frequency that is subjected to harmonic loading before I move on, no. So this is one part out of three parts sa tong discussion karon gabi. Erase. Okay. All right. So nabatay questions and clarifications before we move on. Or wala ka man, no? So medyo sayin pa siguro ni siya. So drain na ta sa harder na part, no? So which is the if ganiha nagstorya ta sa undamped system, now we will be dealing with the harmonic na response, no? Harmonic loading. But sa damp systems na. So which is, well, our differential equation that is governing this type of motion is, we will now include, no, our damping constant. Pero same gyapon ato ang atong forcing function. So more gid atong gi-add, no. So to get the the characteristic equations, no. The characteristic equation charis pa na kong suot. Characteristic equation, it's still kanang sa underdamped na equation, no. So our characteristic equation is U of C of T is, hopefully you can remember, no, kani siya, which I have discussed before, no. This one. Okay? So, of course, I forgot ang kani atong omega kay since damp naman siya, so damping natural frequency na atong istorya. Okay? So, this is our complementary or the characteristic equation. So, we'll be solving for the particular solution, no? So, ang kani siya, we'll be using a particular solution or a trial solution, same gapon before, no, sa ganihan, no. So C1 sine of omega t plus C2 cosine of omega t, no. So we'll be using this pamaagi, no, and then so ako na say derive ang first and second derivative just for completeness lang. So cosine of omega t, and then plus C2 sine of omega bar t. Okay, and then double prime is C1 omega bar squared negative sine of omega t plus C2, this should be negative and then this should be negative, C2 omega squared cosine omega bar t. So kani siya kuwang ko og kani siya. Okay? So I'll stop here, no, because balik na siya sa akong solution earlier. What I'm going to do now is same gyapon, no, we have to substitute all of these three things, kani three na solution into our original differential equation, this one, and then find C1 and C2. No? However, skip na lang ko for the good part na nanay C1 and C2 dahil because it's a very, very lengthy and algebraic na discussion, but I can assure you that our C1 is kanang, where did I derive it? Here we go. So the derivation later on kay mo gawas ang kanina form, no? 1 minus r squared, and then 1 minus r squared to the squared minus a plus di plus 2 epsilon r squared, no? So kani siya ang C1, and then ang C2, which is the second constant, is very similar. 1, it's not 1, it's negative 2 epsilon r over the same denominator. 2 epsilon r squared, no? So kani siyang C1 and C2, but if you want more na kaning explanation asa gini siya, you can actually refer to the notes ni Engineer Gitamondok, no? So particularly in page okay, let me find it here. In starting page 29, no? So starting page 29 up until 31. So kani siya na 3 pages. Okay, mo na ang iyang discussion on okay, how do you get the what you call that, the forcing the C1 and C2. So sa discussion ni Engineer Gitamondok is using the complex na analysis, no, which is I'm going to cover next, no. Pero the C1 and C2 is from here. So ang kani siya na pamaagi is okay. Taas kay yang way of solving it, no. But usually sa atua sa structural dynamics is what we are really interested is usually the amplitude of the response. So the amplitude is usually another fancy way of telling na I just want the total displacement, no, or the deflection for the dynamic analysis. So the pinakadagko na deflection sa akong deflection sa atong beam or sa frame, no. So in this case kay ang kani siya C1 and C2, no, if I'm going to write the whole equation, the total solution, no, the total solution using this na pamaagi, because I'm going to explain the other one, is u of t now is equals to e to the negative kani siya times a cosine of w dt plus net b ups sine okay plus ang C1 can I do this faster? Let's see. So kani siya the C1, no? So I'm gonna copy, I'm gonna paste kani siya plus ang C2. So plus ang C2, no? So kani siya. Copy and paste it here. Of course, kaya ang C1 and C2 is just the constant. I have to add its corresponding na sign, no? So remember, kay C1 is just is parted with sign omega t, no? Omega bar t. So kanisa siya kay na paresat siya sa cosine, no? Omega bar t. Okay, so this one, kanina whole equation, it's kind of hard to get what is the amplitude of our forcing function because we have the forcing function between the sine and the cosine, no? So there's another way that we're going to solve the same differential equation, but we're going to transform it into a what you call kanang mogamit ta sa Euler's or Euler's na method, no? So sa Euler's method is using Euler's method, we can say that our I of WT is equals to cosine of W bar t plus sine of omega bar t. Okay? So, mo na siya ang Euler's relation, no? Or Euler's method, no? Euler's relation. Okay? So, meaning ano niya, we can actually substitute our forcing function, no? So, I'm going to write the differential equation, m u double dot plus k single dot plus c u, mali, is equals to FO e to the I W bar t. Okay? So, mo na ang special na relation, no, using Euler's na method. So, since if you remember, no, atong forcing function is only using sine, no? So, sine. So, if we go back to our knowledge sa trigonometry, so trigonometry review. So, sa complex numbers, right? Sa complex numbers kay kanang or dili siguro sa trigonometry, when we solve for our differential equation, kay mas tuon na lang siya. Usually kay ang atong isolve kay let's say beta t, no? It's usually ang imong imaginary number, which is I, is usually tupad siya sa atong sine na function. So therefore, no? So we have to take note lang ang kani siya, kung magkuha tag solution niya, we will only just consider the imaginary solution, which means that akong unsay kani siya na real solution, ato na i-disregard, and then we will just only accept the imaginary solution. Okay? So muna ang special technique ani niya. Okay, so I'm going to erase this one. We're going to solve our differential equation using this na special relation, no? So, if mo ni atong differential equation, we already know our characteristic equation, no? Same ra gyapon kaniha, no? So the characteristic equation, I'll just copy this one, no? Just for the sake of completeness, gonna copy this one, gonna paste it here. Since it's the same, no? But our particular equation or particular solution will still be using the trial solution, no, sa ato ang undetermined coefficients, no? So that our particular solution will be in this form as well, no? I'm going to include a constant kani. Okay? Oops. Kani siya because we have tungod kani. Alright? Okay. So, if this is our trial solution, we're going to get the first and second derivative. Same gyapon ang story, no? C negative FC, epsilon siya. It should be I. Oops. This is the trial solution. I omega t. So, kani siya, wala isang siya. So, I omega t. Okay? So, since C is constant, and then ang I is also a constant, and ang omega is also a constant, so it's gonna be kani siya. So, that's the first derivative. The second derivative now is U double prime P of T, no? It's gonna be C, ang I, it's gonna be I squared, no? So I squared is just negative 1, so negative here, and omega e to the IWT. So, natin three solutions, no? Which is related to each other, kaya it's just the derivatives of each other. So, we're going to substitute, no, this particular solution, trial particular solution sa to ang original na equation. So, original equation, substitute. So, what will happen now is mass times C, negative C omega e to the I omega t, no? Plus your damping constant times your velocity plus ang ato ang K, which is the spring constant, times ato ang displacement is equals to our forcing function, F O E to the IWT. So, if you guys notice, tanan IWT ma-cancel out because everything is shared, no? Between sa left side and the right side of the equation. So, mahulog siya 1. So, to simplify it, it's negative, kani siya, oops, ako ibalihon na lang, negative CM plus small capital C, small letter C, IW plus K C is equals to FO. So, we want to solve for capital C, no? So, capital C, I'll take it out from the equation, which becomes like this, no? And therefore, ato ang C, no? The C is now FO over negative K, ako na i-positive K minus M of na ko gani siya, no? Nakalimot ko ani. So I'll just correct it later after I write this one. So akong nakalimot is what is kani siya? Just for the sake of completeness. Okay. Okay siya. Let me check. Okay. So this is our C, no? Which is, this is what you call your amplitude. Amplitude. So ang meaning sa amplitude is, this is the pinakadako na displacement, no? Sa ato ang based on our forcing function, no? So mo ni meaning ano niya. Usually ang iyang units is inches or millimeters, usually small units, pero depende, no, kung nag-design di ay tag-bridge basit ang atong displacement K per in terms of meter na, we don't know. So this one is your amplitude. Usually sa mga books, it's usually point it as letter U. So sa Mario Pass, it's a letter U. Okay? So therefore, if we're going to solve for the entire particular solution, no, it's gonna be looking like this, no? FO over K minus M omega squared plus ICW bar, no, times our kani siya E IWT. Okay? So, kani siya, no, we have to, again, no, we have to try to separate the sine and the cosine because we are just interested sa ato ang sine na function, right? Because ang original forcing function is actually based on a sine na function. Let me, sorry, kani siya, sine na function, no? So, what we're going to do is we're going to use a special technique, no, sa using our polar coordinate form. So, what I mean by that is, or what the book means by that is, ang kani daw siya, ang kaning denominator, we can treat ang kani duha, no, kani siya duha is a single term, and then ang kani siya duha is another term. So, it's gonna be something like this. Hopefully you can follow, no? FO over ang kanisya, I'm going to write it in parentheses just to emphasize na it's one singular term na, and then I'm going to add the second term, pero akong gitang tang ang I, no? Okay, and I'm going to square it and then take the square root. Okay? So, ang kanisya is just a resultant, no? Because if we're going to go back sa trigonometry, what we just did is, ang kani daw siya, kaning entire term, this one is the hypotenuse. And then this one is your vertical, and your k minus m omega squared is your horizontal component. So, pwede kani siya na technique, it works, no? So kani siya na-convert ta atong gitangtang ang imaginary number sa ubos. Okay? We want it uh, to factor it out, and this is one way to do it, no? Of course, there are several ways, but this is the most convenient way. So just remember that we use the polar coordinate form. So kani siya usually kay if you go back to Euler's na relationship, no, we have to multiply the EI, and then ang last one is theta. Ang kaning theta, if we go back again, na akong i-erase kay since this is the hypotenuse, and then CW bar ang vertical, and then K minus M omega squared is the horizontal. So the relationship of our theta now, which is what we call the phase angle, no? So we can actually get the relationship by using the tangent na function, no? So CW omega, where's my eraser there? C omega over K minus M omega bar squared, no? So mo na siya ang theta, mo ni meaning sa theta niya. So what will happen now is sa taas, I think I forgot to write this one, no? So kaning duha na terms mag-combine siya each other. Okay? Because same man siya base. So what will happen now is, if we're going to combine it, the particular solution would look something like this: FO E to the unsa man atong common denominator. Okay, ang common ani niya is ang I, no? So I. So we're going to factor out the I. I'm going to write the omega E here minus theta. Okay? Or and then all over the same denominator that we have written. So kani siya the K minus M omega squared plus C omega squared okay. Kani siya, and that's it, no? So if mo na mahitabo, no, if we remember sa Euler's na discussion, no, ang kani siya, we can separate the okay, I'll scroll back up, no? So Euler's na pamaagi is this one, right? Kani siya. So we can now separate the cosine and the sine, no? So we are just interested sa atong sine. So mahitabo ni karon, our particular solution, the correct one now is just FO sine of omega bar t all over K minus M omega squared plus CW squared square root. So kani atong particular solution, no? This is our particular solution, or another way of saying it is, again, our U, which is our amplitude, no? Amplitude factor now will become FO over K minus M omega squared plus CW squared all over square root. This is our amplitude. Amplitude of the steady state motion. Okay? So this is the amplitude. So meaning anak niya, if you solve for this one, it's actually the maximum dynamic deflection, no? The maximum dynamic deflection, the pinakadako na deflection based on the dynamic na loading. Okay? So what we're going to do now is, if we remember earlier, we related our K and M's, no, or omega kani siya in terms of R, the frequency ratio, because again, the frequency ratio is important in the study of structural dynamics. Kaya we can know if our system is in resonance or not. No? So if we're going to replace ang atong omega bar with R, no, the frequency ratio, the amplitude, no, would look something like this, or the whole solution, no. So UST times sine of omega WT minus theta, okay, all over 1 minus R squared plus 2 epsilon R squared, no, and all over square root. Okay, where the tangent of theta, again, is still the rise over run, which is 2 epsilon R over 1 minus R squared. So, kani siya na solution is very similar sa katong solution here. Kani siya. If tagabantay ta is 1, no? ER. So, very, very similar gid siya. Okay? So, what this means now is, well, but I have to define what is UST. So, UST, no, is actually is equals to FO over K. So, which is our forcing function, amplitude of our forcing function divided by the stiffness. Or, if we go back, kung sa may meaning gid anak niya, the force is equals to the stiffness times the displacement. So, mana siya. So, this is what you call your static displacement, no? So, mana meaning sa F over K. So, ang F over K, again, no, is unsay ang iyang static displacement based kung it is acting alone, no? Ang FO is acting alone, and it's not in terms of kanang na-multiply siya sa sinusoidal na function. Okay? So, this one is said to be the static deflection of the spring. So the spring is the stiffness, no, acted upon by the force FO. Okay? So again, if you remember, ang epsilon is actually your critical damping, no? So epsilon is your critical damping, which is the critical damping ratio, which is C divided by CCR, no? So the damping rate, the damping constant divided by the critical damping constant, which is, we need to solve this one, right? And then ang R, just to recap, is the ratio between the forcing functions frequency divided by the natural frequency of the building, no? So this is what you call the frequency ratio. Okay? So, magtaas na kayo siya, but the solution for everything, no, is we have to add the transient na response and the steady state response. So the transient response is this one, no? A cosine of omega dt, so the damping constant, plus B sine of T K plus ang everything here. So plus this one. So gonna be lazy, cut me siya, agapi di ay, and then somewhere I'm going to paste it here. Okay? So this now, kani siya, atong equation now is our complete solution, no? Complete solution for a structure, a single story na structure na naa siya damping involved na. Okay? So, ang important thing here to keep in mind is, again, aside from going back, no, we can solve for A and B, right? We can solve for A and B in terms of kanang initial value problem, no? So usually times equals to 0, displacement is equals to 0. So if we're going to do that, you can get the values of A and B, right? Pero dili ra ko mag solve ana kay it's actually it really depends on the problem. So as long as you know how we derive this equation, no matter unsa ang mga um, problem, no? Bundakan sa toa, as long as we can derive it, then we can actually solve for A and B. So which is we have one example later, no? So I want to introduce now what you call a dynamic magnification factor. So kanina introduction of the dynamic magnification factor, no? It's just no? It's just a relationship or the ratio between your amplitude of your dynamic response divided by the response due to the static, no? So which is if we're going to do the math, it's actually 1 over the square root of 1 minus r squared plus 2 epsilon r squared or kanisha, right? So it's just a unit. A factor man siya. So kinang 1 unit na siya. Okay? So nawagtang ang iyang sign omega t minus theta. Okay? So unsa may purpose ket ani niya ngano na siya importance. Ang kani siya dynamic magnification factor, if I'm pretty sure all of you nakapasar kang engineer Dukay. So if sa bridge man gyud, if you remember, nagbutang mo og impact factor, which is usually mga between 1.5 to 2.0 or greater, no? So kani si impact factor, no, is just similar to this one or maybe the same, right? Kay moto siya nag-design ta sa atong roads or atong bridges, kay once mo agi atong mga sakyanan mo, actually ang atong bridge is actually a dynamic na problem, okay? So but we converted that dynamic na problem into a static one. But that static to convert our dynamic problem into a static one, we actually use what you call an impact factor. But in this case, it's actually called the dynamic magnification factor. So ang meaning anak niya, alright, ang meaning anak niya is, if I'm going to rearrange these terms, no? So makita mo ani karon kay if natay deflection daw of your static deflection, no? For example sa beam kay PL over 14 EI or 5 over 384 double L to the 4th over EI, no? So that's your static deflection. You multiply daw your dynamic factor, right? So dynamic factor, you can get your estimated dynamic amplitude, no? So meaning anak niya, you can actually get your maximum deflection of your dynamic na loading based on your static na loading times some sort of a factor, which is what we call a dynamic factor. Okay? So mo na yung meaning or importance ani niya when we design dynamic na structures na kanang na ay machine, no, na ay vibration involved, no. So if we don't want to deal with the dynamics, structural dynamics of the problem, no, of the structure, you can just introduce a dynamic magnification factor. But the problem now is what values do we need, no? What values do we actually use, no? So it really depends, no? So I have here a study, no, kanang quick. I'm going to show you my other screen. So there's a study sa to, I'm going to share everything, no. There's a study sa usa ka journal article, no, na nakahimo siya og study unsa magid gamiton na magnification factor. So the use of dynamic magnification factor in the dynamic analysis of frame structures, no. So sa unsa na siya? Asa siya napita? I think it's na Nigeria, masigon siya na area. So ang kani siya na paper, it describes na okay, I can design my structure using the static procedure, but I'm going to use a dynamic na amplification factor, which is the D, no. So based sa iyang discussion of results, okay? So, ang iyang gibuhat first is nagsolve siya ang static response, no? So, katong what we have learned na moment distribution method or tawag ani portal method and whatever, no? And then, iyang gi-solve ang iyang free vibration because we need the omega, right? So, iyang gibuhat next is nag-solve siya sa dynamic response factor using the force vibration analysis. So, what we just did, all of that, no? So, iyang gikuha is, okay, pila ang displacement and then pila sa iyang bending moment and shear and axial loading, no? So, usually, what we are interested is actually this dynamic and static displacement because the dynamic magnification factor kanisha is just the ratio between the joint displacement, no? Displacement sa dynamic divided by the displacement sa static. Just to prove a point, no? I'm going to open a calculator. What he did is the dynamic na displacement 0.67 yang i-divide by 0.5 which is ang Gauss answer 1.34 mo yung gigamit, no, na dynamic magnification factor. Pero sa iyang experimental setup, there are 4 frames, no? So naki-frame 1, frame 2, so single story, 2 story, 3 story, and 4 story. So that 1 story to 4 story kay muusab-usab gid iyang dynamic na factor, dynamic magnification factor. Even though unsa siya nag-apply ra siya kana tawag ani kanang forcing function lang which is a sinusoidal na forcing function. Right? So to cut the long story short, ang nahitabo ani karon kay if you're going to apply the dynamic na factor, ang mahitabo ani karon kay its result, no, is equals to the once you solve our system using that structural dynamics, same ra siya ang result sa static na method, no? So mo na ang nice ani niya. Okay? So we're to go back, no? So meaning ana niya what we have solved everything, no, it's actually to derive aside from knowing the background of the structural dynamics of a harmonic na force, then apply siya sa damp na system, we actually derive our dynamic magnification factor, no? So moto siya mga uban engineers kay dili sila dili sila mo go deeper sa structural dynamics because of this one, the magnification factor. But what I have shown you earlier kay those factors kay kung single story kay 1.4, then sa second story kay ilan ito mga 2.3, and then sa 3 stories kay 3.7, no? So the 4 story kay nagpaling sa 2. So ang kana siya kay dako kay na siya na question pa what dynamic magnification factor that you need to use sa pag-design sa bridges, no, or dams or whatever, no? Usually from experience, you can actually assume your dynamic factor based on experience, usually sa mga senior structural engineer, no? So ingon si engineer mo na gamitan lang 3 or gamitan lang siya 2 because he already solved it before, no? So if wala ganin wala tayong experience na niya, what you can do is read books naman siya suggested dynamic magnification factor, or just do the hard way, just solve na lang, which is okay, diba? Kay it's good to practice your differential equation para makasutisan mo na sa akong work nagamit ko ODE, ordinary differential equation. Okay, so this discussion moto siya ang theory sa atong discussion karon, no? So mag-break siguro for 5 minutes, mag-inom sa tubig or just stretch kay we've been at it for 1.5 hours just to discuss, no, sa atong theory. So mag-stretch sa ta, and then let's come back here at around 8 p.m. and then we'll be discussing sa example problem which is coming from the book, no, pero I'll just show my similar solution, but we just follow along sa book, no. So sige, 5 minutes break, stretch sa ta, and drink water, or if you need to pee or poo, now's the time, no, and then let's come back by 8 p.m.